Let's take a look in a little more detail how we can apply what we've learned about velocity and acceleration to motion that's in two dimensions. So these could be any two dimensions. They could be two dimensions parallel to the ground, or you could have one vertical dimension and one horizontal dimension. We could involve any of those different possibilities. So at the bottom of the slide here, we have the path followed by a particle. So this might be an overhead view of a road, and the three black dots represent a car, for example, at three different moments in time as it drives along the road. So the first thing in two dimensions to know is that the velocity is always going to be in the direction of motion. And so that means it has to be tangent to the path. Tangent line is a line that passes through the point of interest without crossing the path at that same location. So here is the tangent line for the first point. You can see it passes through the point but does not cross the road, if you like, at that same place. Here's the tangent line for the second point, and there's the tangent line for the third point. So whichever direction the car is going, whether it's traveling generally to the right or generally to the left, its velocity when it passes those points has to be along that tangent line. So let's imagine that the car is actually traveling generally to the right. So in that case, I've drawn in some velocity vectors to show the velocity of the particle at those specific moments. Now remember, the acceleration can be in any direction at all. It's the direction of the acceleration compared to the velocity which is going to tell us how the velocity is changing. Or if there is no acceleration, that'll tell us that the velocity is a constant. So there are a number of possibilities. In this particular case, imagine we have the acceleration in the same direction as the velocity. Again, if you remember, if the velocity and the acceleration are in the same direction, that means the object is speeding up. If the acceleration is the exact opposite direction as the velocity, then that would mean the object is slowing down. In both cases, without turning. On the other hand, in this case, we have a situation where the acceleration is perpendicular to the velocity. And by the way, you can't look at these pictures of the velocity and tell from that alone what the acceleration is going to be. This is something I'm adding that you'd have to know from other information. But in any case, here we have an acceleration that's perpendicular to the velocity. And if you remember, in that case, the object is turning but not changing speed. So in this case, the particle is turning to its right because that's the direction of the acceleration. Now, of course, it's possible, like in this final situation, that the acceleration is neither parallel nor perpendicular, in which case the particle is both turning and changing speed. So basically what we need to do is, if we have a velocity and an acceleration vector at a moment in time, we have to figure out the components of the acceleration along the line defined by the velocity. So in this case, there are those two components. There is a component of the acceleration that's parallel to the velocity, and there's also a component that's perpendicular to the velocity. So again, think of the velocity vector as defining a line, and that's our axis. We want to find the components of the acceleration parallel and perpendicular to that line. So here's the deal. The parallel part of the acceleration has to do with changes of speed. So if there is a parallel component, if there is a component of the acceleration parallel to the velocity, then the particle is changing speed. If that parallel component is the same as the velocity, it's speeding up. If it's the opposite direction, it's slowing down. The perpendicular component of the acceleration, if there is one, has to do with changes of direction. And so in general, whatever the velocity and the acceleration vectors look like, we can break the acceleration up into components and figure out what's happening to the speed and what's happening to the direction. In particular, these are the 5 possibilities. So if something is speeding up only, if we define the angle between the velocity and the acceleration to be theta, if something is speeding up only, theta will be 0 degrees. The acceleration and the velocity will be in exactly the same direction. If it's speeding up and turning, which is the case in the figure, then the angle will be somewhere between 0 and 90. If it was turning only with no change of speed, so there was only a perpendicular component, the angle would be 90. If it was slowing down as it turned, then the angle would be somewhere between 90 and 180. And finally, if the angle was 180, so that the velocity and the acceleration are all along the same line but in exactly opposite directions, then it would be slowing down only. So by looking at the velocity and the acceleration, looking at the angle between them, we can actually now interpret in detail exactly what that's telling us about the object's motion.